Hey guys, today's lesson is going to be on the rational root theorem. It's section 4 of chapter 2, and we're going to be using this rational root theorem to discover zeros of polynomials. Anytime that you have a polynomial, you can discover all the possible rational zeros by using this rational root theorem. So let's first understand what a rational zero means. A rational number, again, is a number that can be written as a fraction. So numbers like 1/2, or 2/3, or 0.5, or 6. All these types of numbers are rational. Irrational numbers are numbers that you can't write easily as a fraction. So for example, the square root of 2. If we were to approximate that as a decimal, it would go on forever and ever, and you couldn't write that decimal as a fraction. So anytime you square root a non-square number, that's an irrational number. Or anytime you have the idea of like pi or e, those are examples of irrational numbers. So we're not saying that these are all a way to find all the zeros of functions, because these numbers can be zeros. You can have the square root of 2 be the zero of a function. But if we want to just find the rational zeros, the ones that are nice, pretty numbers, then we can use this rational root theorem. Alright, so let's go ahead and talk about what the rational root theorem says. The rational root theorem states that if you find all of the factors of the constant term and all of the factors of the leading coefficient, then you can use those to list all of your possible rational zeros. So what we do is we list all the factors of our constant term. We call that p. So all of the factors of 1 would be positive 1 and negative 1. And so we kind of shorten that to and just say plus or minus 1. And we take all the factors of our leading term, which we call q, and our leading term coefficient for this one is 1, so that would be plus or minus 1. And then we divide them. So the possible rational roots, or the formula for it, is always p over q. So if I was to list all my possible rational zeros for this problem, it would be plus or minus 1 divided by plus or minus 1. And so you can see either way you divide this, that 1 divided by 1 or negative 1 divided by 1 is always just going to be plus or minus 1. So that means there are only two possible rational zeros for letter A. So let's try those two out and see if they work. The fastest way to test them out to see if they work is to do synthetic division. So I'm going to say, okay, if I synthetically divide 1 into my coefficients are 1, 0, 2, and 1. Let's see if we get 0 at the end. So we're going to do our synthetic division. Bring down the 1. 1 times 1 is 1. 1, 3. 3 times 1 is 3. And 3 plus 1 is 4. So if you don't get 0 for your remainder at the end, that means it's not a 0. So 1 is not a 0 for the function. We just need to try negative 1 now. So we'll do negative 1, and we'll plug that into 1, 0, 2, and 1. Negative 1 times 1 is negative 1. Negative 1 plus 0 is negative 1. Negative 1 times negative 1 is 1. Plus 2 is 3, times negative 1 is negative 3, plus 1 is negative 2. So this one isn't a 0 either. So if you've tested all of the possible rational zeros and none of them work, then there are no rational zeros. There are other zeros, they just happen to be irrational numbers. And you could get those using your calculator. Okay, but that's not what they're asking here. They just want us to determine how many of the possible rational zeros are zeros. And for this one, there were none. So let's try one where there are some rational zeros, so you can see how that works. And this one has more factors to it too. So first let's identify what p is. P is the factors of our constant term, which would be all the factors of 9, which would be plus or minus 9, plus or minus 3, and plus or minus 1. Those are all the factors of 9. And then our q would be the factors of our leading term, which luckily again is just 1. So now if we find all of our possible rational zeros, we do p divided by q. Dividing each of these terms by positive or negative 1 is just going to leave it as positive or negative 9, positive or negative 3, positive or negative 1. So these are the terms that we're going to check in our synthetic division and hope that we get a 1, or hope that we get 0 at the end for. So I always say start with the easiest ones first, because they kind of have an equal chance of working anyway, so you might as well use an easy number that you can plug in quickly. So I always start with 1 and negative 1. Our coefficients are 1, 4, negative 12. Oops, be careful. We're missing a term here, right? There's no x squared term, so I need to put a 0 down. So there's my x squared, negative 12, and negative 9. So we're going to bring down the 1. 1 times 1 is 1, plus 4 is 5, times 1 is 5, plus 0 is 5, times 1 is 5, plus negative 12 is negative 7, times 1 is negative 7, we get negative 16. So the 1 didn't work. Let's try negative 1. 1, 4, 0, negative 12, negative 9. Carry down the 1. 1 times negative 1 is negative 1, plus 4 is 3, times negative 1 is negative 3, plus 0 is negative 3, times negative 1 is 4. Oops, not 4. Times negative 1 is 3, plus negative 12 is negative 9, times negative 1 is 9. There we go. And so we get 0 for our final term, which means that negative 1 is a factor. That is a rational 0. So we could write this in factored form, but they want us to try to find all possible rational zeros. So now what we can do is we can say, all right, this is my depressed polynomial down here. I'm going to take out the negative 1 that I know is already a factor. X minus 1 is a factor. What we have left here will help me find any other factors that I have, because I'd rather take a shorter depressed polynomial than having to keep use this long big one. So now I can use 1x cubed plus 3x squared minus 3x minus 9 and try to find factors of that polynomial. We can use our same list that we had before, and if we've eliminated any of our possible choices, there's no use in trying them again. So I still have to check 3, negative 3, 9, and negative 9. And technically I should check negative 1 again, because it could have multiplicity and work again. So I'm going to go ahead and do that first. I'm going to check negative 1 again. We're going to synthetically divide negative 1 into our coefficients of our depressed polynomial, which is still just 1, 3, negative 3, and negative 9. So I carry the 1 down. Times negative 1 is negative 1, 2, negative 2, negative 5, 5, negative 4. Okay, so negative 1 is only a 0 once, so it doesn't have any multiplicity. Let's try the next smallest number, which would be 3 and negative 3. So if I synthetically divide 3 into this, that's 1, 3, negative 3, negative 9. Carry down the 1. That's going to be 6. It's going to be 18, looks like it's going to be too big. Yeah, that's 15, that's 45. Way too big. So 3 isn't going to work. Let's try negative 3. Negative 3 into 1, 3, negative 3, and negative 9. It's 1, negative 3, 0, 0, negative 3, 9, 0. Perfect. So we got our second rational 0. It's at negative 3, so that means the factor is x plus 3. And the depressed polynomial we have left now is 1x squared plus 0x's minus 3. So at this point we could pretty much just solve for the zeros of this polynomial, x squared minus 3. We could just solve that and see, well, x squared minus 3 equals 0. If I try to solve that, what kind of zeros do I get? I get plus or minus the square root of 3. Those are not rational, those are irrational zeros. So the only two rational zeros are at 1, 0, and negative 3, 0. Okay. There are four total zeros, it's just these two are the only rational ones, and then your irrational ones are at square root of 3, 0, and negative square root of 3, 0. So if we're strictly doing what the instructions say, the instructions just want us to find these two. But we should be able to find these as well. Okay, so I'll give you 2 to try on your own. Okay, so here are your solutions. If you found all the possible rational zeros for 1a, they would either be plus or minus 2 or plus or minus 1. Those are the only possible rational zeros for that function. And the first one that you tried, if you tried 1 like I recommended, that was the very first one that worked. So 1 is actually the only rational zero. The way I could tell that without going any further is that if I looked at the quadratic that was left over, You don't really have to do synthetic division with the quadratic. All you have to do is try to factor it. If you can factor it, then those factors would be your other rational zeros. If you can't factor it, then there are no rational zeros left. You could possibly have zeros, but to solve for those you'd have to use either the quadratic formula or some graphing feature. So since we're only looking for the rational zeros, I stopped right there. Now for 1b, we had quite a lot of more possible rational zeros because instead of our constant being a small number like 2, our constant was negative 30. And so when I listed all the factors of negative 30, there were quite a few. Luckily, we had to divide that by just q, which was 1. So my possible rational zeros were plus or minus 30, 15, 10, 6, 5, 3, 2, and 1. And so the process would require me to go through and check all of those. Luckily, the first one that I found, 1 and negative 1 didn't work, but 2 did. So 2 is my first rational zero. And so once that's synthetically divided out, I was able to take out x minus 2, and then this was my leftover polynomial. Now, you could have continued the process and kept going through the list, trying to find the other possible zeros, checking them to see if they work, but I noticed that I could actually factor this cubic 4-term polynomial because I saw that it was factorable by parts. So I factored x squared out of the first 2 terms, and I factored 3 out of the second 2 terms, and I noticed that I got x plus 5 and x plus 5, which I factored out, leaving x squared plus 3. Now my zeros for x squared plus 3 are imaginary, so those don't get included in my list of rational zeros. Instead, I've got the 2 I started with, and I found another one, negative 5. So those are my only 2 rational zeros, 2, 0, and negative 5, 0. Okay. The second example, the only difference is that your leading coefficient is not going to be set equal to 1. So we're not going to go through and do the entire synthetic division. We'll practice that more in class tomorrow. But I did want to practice with you making the list of possible rational zeros, because that's part of the problem, is to actually list them. So we start with our p again. P is all of the factors of 8, the constant. So that's plus or minus 8, plus or minus 4, plus or minus 2, and plus or minus 1. And q would be plus or minus 3, and plus or minus 1. So the factors of your leading coefficient. So to find all the possible zeros, possible rational zeros, we have to do p divided by q. So I always just take it one at a time. I do 8 divided by 3 is plus or minus 8/3. 4 divided by 3 plus or minus 4/3. 2 divided by 3 plus or minus 2/3. These are all rational numbers, they're fractions. And 1 divided by 3, 1/3. And then I'll do all of them divided by 1 as well. So 8 divided by 1 is plus or minus 8, plus or minus 4, plus or minus 2, plus or minus 1. Okay, and so we would have to go through now and check each of these numbers, positive and negative, to see which ones are possible or actually zeros for this function. Again, always start with your easiest ones, and in class tomorrow I'll give you some hints to help you find them a little bit faster than having to go through and do this, 16 different times. Okay? So for right now, I just want you to practice listing your possible rational zeros. You don't actually have to find which ones are zeros, just list the possible ones for A and B. Okay, so for 2a, I listed all of the possible factors for 36, and then all of the possible factors for 2, and then I divided all of the p's by the q's. So 36 divided by 2, 18 divided by 2, 12 divided by 2, 9 divided by 2. And so you get this really long list. Of course, all of these also divided by 1, they stay the same. And then all of them divided by 2. Now some of them repeated themselves. So down here, if I got 18 again when I divided 36 by 2, you don't need to list it twice. So I just canceled out all the repeats down here. But then I also got 9 halves when you divide 9 by 2, 3 halves when you divide 3 by 2, and 1 half when you divide 1 by 2. Those did not repeat. Those were new ones. So there's all of your possible rational zeros for 2a. And then here are all your possible rational zeros for 2b. They're either going to be plus or minus 21, 7, 3, or 1. Or if you divide them by 3, you got a couple of repeats, but you also got 7/3 and 1/3. Okay, that's it for this lesson. This is a class we're going to be doing. It doesn't look like much, but they do take a while because you have a lot of factors to check. So I will see you guys in the morning. Have a good one.